Welcome back to another Forge College Explainer. Okay, so if you were with us for the previous lesson on designing advanced structs and mappings, you know we've built some seriously intricate data models. But before we just send them out into the wild, we really need to make sure they actually work, right? Welcome to the wind tunnel. Today, we're testing those complex structs and mappings you designed to ensure your smart contract doesn't, spontaneously explode on the launchpad. We're going to keep things light, but trust me, the bugs we're hunting today? No joke. In Web3, a single missed validation can literally mean millions of dollars permanently locked or drained. Getting this right is absolutely non-negotiable.
Let's just quickly look at our engineering blueprint for today. We've got 5 main stops. First, setting up our wind tunnel. Then testing mechanics, hunting down the gremlins, building the inspector's log, and finally, the golden rules of testing. Let's jump right in.
All right, Section 1, the wind tunnel, setting up our test environment. Before we optimize anything or even think about gas costs, we've got to put our contract into a secure, isolated local environment to verify structural integrity and data handling.
So what exactly is a struct state transition? Basically, it's the verifiable change in your data. When you call a function, does the struct actually update the way it's supposed to? We're tracking exactly what happens when our mechanical parts move. Like if a struct is supposed to toggle an active flag to false, we better be 100% sure that flag actually flipped. In Solidity, structs pack data tightly together to save space. That's incredibly efficient, but it also means a rogue function can easily overwrite the wrong variable if you aren't paying close attention. We need to rigorously test these transitions. We want to make sure that when one gear turns, it doesn't accidentally strip the teeth off the gear right next to it.
To spin up this wind tunnel, we're definitely not testing on a live network just yet. Instead, we'll initialize a local test suite using Hardhat, Ethers, and Chai. This stack is an industry standard, and for good reason. It gives us a safe, lightning-fast sandbox to run our unit-level checks. We can fire transactions and instantly inspect the aftermath without spending a dime on real gas. Think of Hardhat as the testing engine itself, kind of simulating the blockchain right on your machine. Ethers? That acts as the steering wheel, letting our JavaScript talk directly to the smart contract. And Chai is basically the diagnostic dashboard, letting us make powerful assertions about what just happened. Together, they give us complete control.
Moving on to Section 2, testing mechanics, validating structs and mappings. Let's see how our core functions actually hold up under pressure when we start throwing data at them.
Now, this technical spec sheet perfectly lays out the precise behaviors and expected outcomes we absolutely have to validate. Take create record, for example. The expected outcome is that the record fields precisely match our initial inputs, and crucially, our owner mapping contains the newly generated ID. For deactivate, the first call has to successfully set the active flag to false. But, and this is key, the second consecutive call should trigger a revert to prevent state manipulation. And for array manipulation, we've got to verify that values persist across reads and the length stays completely consistent. We're mapping out the exact mechanical behavior we expect from our structs and arrays, literally leaving nothing to assumption here.
So how do we actually execute that plan? Well, just like running a machine sequence, our local test workflow follows 4 distinct steps. First, we initialize the project and deploy the capstone model to our local Hardhat network. Step 2, we send a transaction to create or modify a record. Third, we read the resulting struct and mapping state back from the contract. And finally, we meticulously assert equality between our inputs and the stored data. It's a simple, methodical, and entirely necessary loop. Deploy, execute, read, verify. You just do it over and over until the machine runs flawlessly.
A really crucial concept here is maintaining what we call mapping consistency. Think of your mappings as internal filing cabinets that link an owner's address to their array of record IDs. If an ID gets deleted improperly or duplicated, your entire filing system just falls apart. Imagine a scenario where user Alice tries to withdraw her assets, but due to a mapping error, the system points to Bob's ID array instead. That is catastrophic. We have to ensure these invariants, ID uniqueness, reference integrity, correct subset ownership, stay perfectly synchronized throughout the entire lifecycle of the contract. If the mapping is out of sync, the contract's reality is completely broken.
All right, Section 3, the gremlins, hunting down edge cases. This is honestly the fun part. It's where we intentionally try to break the machine by hunting down edge cases. We want to find the weak spots way before a malicious user does.
Take a look at this question. What actually happens when you stuff 100 items into an array in your smart contract? Asking what happens when we push the system to its absolute physical limits is exactly how we uncover loose cogs. A massive array might seem totally fine in theory,
But remember, every single computation on the blockchain costs gas. If you have a loop that iterates over a massive unbounded array, it could eventually require more gas than the block limit allows. When that happens, the transaction fails, and any tokens or data tied to that function become permanently locked. No way around it. So we test these limits locally to make sure we don't accidentally create a digital black hole on the mainnet.
Your job as a Web3 engineer is to aggressively hunt down these 3 specific gremlins. First up, empty string ghosts. What happens if someone submits whitespace-only labels? Does the contract just accept a blank name and pollute our clean dataset? Second, array overflow explosions. We need to push those array sizes to their extremes to catch those out-of-gas errors we were just talking about. And third, duplicate ID collisions. This is testing what happens if your deletion semantics fail. Like if an item is removed, does its ID get improperly reused? Does it become a weird orphaned record floating in your storage? You have to aggressively stress test all of these scenarios.
And how do we catch these gremlins? We use something called a revert assertion. See, we aren't just testing for success, we're actively testing for failure. A revert assertion proves that our contract safety valves shut down the operation safely when attacked with bad data. If I feed the contract a blank label, I don't just want the test to fail gracefully, I want the test to verify that the contract intentionally throws a specific error message and stops the transaction dead in its tracks. Ensuring your contract fails exactly when and how it's supposed to is literally just as important as ensuring it succeeds.
Moving on to Section 4, the inspector's log, building the debug report. And hey, documenting your software crashes isn't just boring homework, it's compiling an essential engineering logbook.
Your markdown debug report needs to contain these exact sections. You've got to log your environment configuration, your overarching test plan with expected outcomes, the actual terminal output snippets, the edge cases you discovered, and your specific recommendations for remediation. By capturing failing stack traces and contract state snapshots, you're creating a clear roadmap. It's not enough to just say, oh, the test failed. You need the black box data. You need the exact conditions at the exact moment of failure so you can actually fix the issues rather than just, guessing what went wrong in the wind tunnel.
Because sometimes what you expect simply isn't what happens. You might expect a safe revert where the contract yells label required, but in reality, you observe that the contract happily swallowed an empty string and stored it in the blockchain forever. Oops. Documenting this precise discrepancy signals a vital need for a new require statement or custom error in your code. The debug report bridges the gap between what we theorized in our design phase and what actually happened when the rubber met the road. It literally turns failures into highly actionable engineering tasks.
Finally, Section 5, Golden Rules, the 3 principles of testing. As we get ready to leave the wind tunnel, let's lock in the overarching principles that should guide your engineering mindset. Here they are, the 3 golden rules. Number 1, always verify your structural shape and invariants. Check that the data is strictly equal, and check that mapping memberships make total logical sense. Number 2, treat finding those edge cases as your main job, not an afterthought. They're first-class deliverables. The happy path is easy. The edge cases are where the real engineering happens. And number 3, prefer explicit assertions. Don't just assert that a test fails, assert exactly why it fails by checking for specific revert messages and state snapshots. This makes your fixes actionable and future-proofs your code against accidental changes.
So, where does all this rigorous testing actually lead us? Well, next up is optimization and error handling. We're taking the exact remediation notes from today's debug report straight into our next lesson. Now that we know our contract is behaving correctly and we've spotted the weak points, we can safely tighten our validations and optimize our storage packing without breaking the core logic. Testing gives us the confidence to refactor. Actually, without these tests in place, optimizing your code is kind of like trying to change the tires on a car while it's driving down the highway. Not recommended.
So I'll leave you with this question. Is your smart contract really resilient enough for the real world? Have you tested the state transitions? Check the mapping consistency and hunted down all those gremlins. To make sure your smart contracts are truly bulletproof and to explore more Web3 engineering tracks just like this one, visit us at forge.college. I'm your host for this Forge College Explainer, and I will see you in the next lesson. Happy testing!